Hello, everyone. My name is Greim. I'm a class of 1998 graduate from the Physics and Astronomy department, and after spending 20-something years in industry, I'm back at the college working on my master's degree in the Data Science and Analytics program. I'm sorry I can't be there with you in person today. I am presently having a root canal done. Instead, I've provided this pre-recording of my talk. My only hope is that you are having a better time than I am right now. All right, I'm going to be speaking with you today about research for my master's thesis, which is on using deep learning to assist in the discovery of exoplanets. So, what is an exoplanet? An extrasolar planet is any planet orbiting a star other than our sun. And while we've long thought they existed, and we now believe that most stars in our galaxy have multiple planets, the first exoplanet discovery didn't occur until the early 90s. It turns out finding exoplanets is inherently difficult. That's because stars tend to be very large and very bright, and the planets orbiting them tend to be much smaller and not bright at all. Add to this that stars are very far away from us, and you can begin to see that their planets may be pretty hard to detect. But astronomers are a crafty bunch, not usually deterred by needle and haystack problems, and they have come up with a handful of very clever techniques for inferring the presence of exoplanets. In fact, only very few of the thousands of exoplanets discovered so far were found by directly imaging them. And as an aside, one expert in the direct imaging technique for exoplanet discovery is our very own Professor Joe Carson. I'm going to be discussing one of these techniques today called the transit method, which, in terms of numbers of confirmed discoveries, has been by far the most successful. The transit method works in situations where a stellar system is oriented in such a way that we see it nearly edge on. Much like our own solar system, planets tend to orbit around their host stars in a fairly flat disk. When we look at that disk from the edge, so from within the same plane, we can expect to observe the planets periodically passing in front of their host stars from our vantage point. When they do, they block out a tiny amount of light from the star. How much of the star's light they block out is a direct consequence of how large the planet is relative to the star and how close it is to the star. Generally, it's a very small fraction of the star's light. Think of watching a car's headlamp dim lightly as a moth passes in front of it, and all of that is happening many miles away from you. That's roughly the scale of the problem we're working with, and so we require a very sensitive instrument that can detect very subtle changes in the star's brightness. As we monitor the star over time and collect measurements of its brightness, we build what astronomers call a light curve. From the U-shaped dip in that curve corresponding to the dimming caused by the planet, we can infer details about the planet-star relationship in the system. And if we already have information about the star from other studies, such as its size and brightness, we can infer properties of the planet from that light curve. How large is the planet? How close is it to its star? What is its orbital period? So clearly, we need a sensitive instrument to make very precise measurements of the star. And generally, that's best done from space so we don't have to deal with all the nuisances that afflict ground-based observations. One of the reasons the transit method has been so successful at finding exoplanets is because NASA designed, built, and launched the Space Telescope specifically for that purpose, the Kepler Space Telescope. Kepler stared at a tiny patch of the sky incessantly for over 4 years and took measurements of the more than 200,000 stars in its field of view roughly every half hour. This generated high-quality light curves with 70,000 brightness observations for each star spanning the 4-year mission. What an incredible data set. But can you imagine being an astronomer or even a small team of astronomers assigned the task of analyzing almost 250,000 light curves? Kepler, as well as its cameo mission dubbed K2 and subsequent space telescopes, such as the TESS mission, are generating an immense treasure trove of high-quality data for astronomers to analyze. In fact, the absolute deluge of data that modern astronomers are being inundated with is forcing an increased reliance on automated processing and analytics techniques. And this is where machine learning comes in. Let's take a brief segue to discuss what machine learning is. At the same time that astronomy is producing an explosive amount of data from large-scale surveys, computer scientists and mathematicians have made great strides in both the efficacy and accessibility of data science techniques. This fortunate problem and its solution evolved contemporaneously. How nice. Machine learning is a type of artificial intelligence technique wherein a model is trained automatically through its direct experience with data. These algorithms build a model based on sample data known as training data in order to make predictions or decisions without being explicitly programmed to do so. Deep learning is a special subset of machine learning that utilizes architectures based on artificial neural networks. These architectures are generally designed for specific skills and have multiple layers of obfuscated transformations of the data. A convolutional neural network is one of these types of deep learning architectures. It is especially good at extracting information that relies on spatial or contextual awareness, such as image recognition. An important part of being a data scientist is to have, at minimum, a literacy in these techniques, and more often, an expertise in applying them to real-world problems. When the training data includes the correct answer, we call this supervising. So, for example, a model can be trained by showing it a bunch of light curves and telling it whether each one represents an exoplanet transit or not. For each training case, the model makes slight adjustments to its parameter to get a little better at guessing the right answer, which it is provided. Provided enough quantity and quality of training data, the model can learn to guess the right answer. You then show the model data it didn't get to see while it was learning and have it guess the answer. Since you still know the right answer, this is part of your training data after all, you can evaluate how well the model learned. This gives you some indication of how good the model will be at predicting answers to new data. Then, ultimately, the goal is to set the model loose on data that neither it nor you have ever seen before or know the right answer to, and have it make guesses that you can be reasonably confident in. An astronomy postdoc by the name of Andrew Vanderberg and a Google AI engineer named Chris Chalou teamed up and were the first to apply convolutional neural networks to the problem of exoplanet detection, and they were quite successful. In my work, I follow their approach in an effort not only to reproduce their results, but also attempt to improve on them by providing the model with additional information. So, as discussed before, a machine learning model not only needs a sufficient amount of training data, it also needs a very good set of training data. Often, the data is more important than the architecture of the model. And as any data scientist will tell you, 80% of their efforts are consumed with data preparation. So I'll spend the little bit of time we have left today to talk a bit about the steps we go through to prepare the raw light curve data and make it usable for a convolutional neural network to train on. We'll take an example Kepler target and look at its raw light curve spanning the entire 4 years of the mission. And to make things a little easier to understand, we'll concentrate on just the first portion of the data and zoom in on that. Since we're looking at the brightness of the target star on the y-axis over a period of time on the x-axis, we should be a little perplexed by the sudden jumps and trails in the light curve. After all, we don't believe the star really behaved like that. These discontinuities in the raw data are instrument artifacts, and thankfully, the very talented Kepler team has already developed a processing pipeline to remove systematic and instrument errors and provide us with a cleaner light curve. This Kepler pipeline brightness data will be our starting point. So even with the instrument systematics removed, we still see quite a bit of variability in the star's brightness. But that's okay, we expect to see that since stars generally do dim and fade for multiple reasons. For example, some stars pulsate, others have star spots and flares, and yet others have stellar companions. For our purpose, however, we're interested only in how much the star dims as a result of a relatively short-lived planetary transit. So we'd like to remove this longer period stellar variability and look only at the relative dimming from a transit. To do so, we can model the star's inherent variability by fitting a curve to the data and then dividing out that curve. Here, we are using a spline. Now, this is a fairly involved and complex process because you want to avoid deleting your planet's signal while you remove the star's signal, but that's a subject for another entire talk in itself. Having fit or modeled a series of splines for the entire light curve of the target star, we can normalize our data by dividing out the spline from the absolute brightness values. This yields a new, flatter light curve that shows the star's relative brightness over time and makes it much easier to spot dimming caused by planet transits. You can probably pick out one or two obvious ones already. Let's stretch out our smaller view of this target star in the very early days of the Kepler mission and take a closer look at the normalized light curve. This light curve contains the transits of 5 different planets. 4 of them are shown. Can you spot the last one? Do you think the convolutional neural network will be able to? The zoomed-in views of the planet's transits are referred to by Shalou and Vanderberg as the local view, and together with a slightly more zoomed-out global view, represent the input for their CNN. In my work, I will be presenting the CNN with separated views of odd and even numbered transits for each candidate with the hope of improving its ability to distinguish between an exoplanet transit and a common false positive caused by binary stars. But that is a subject for another talk since we're out of time. Thank you very much for your time.